All right, so last time we rewrote the Gauss-Bonnet theorem and the Hitchin-Thorpe signature theorem in dimension 4. And in fact, the Gauss-Bonnet theorem had an interesting consequence observed by Bishop and Goldberg, namely that if you have an Einstein manifold, then the Euler characteristic of that thing must be non-negative. And so this is an obstruction to the existence of Einstein metrics. And we wrote down a few examples of four manifolds with negative Euler number, so those cannot have Einstein metrics. And that's interesting because in higher dimensions, as I mentioned, no such obstructions are known. Today, we want to start by refining this observation of Goldberg and Bishop. And this refinement is called the Hitchin-Thorpe inequality. So let me write this down. So this was studied independently by Hitchin and Thorpe in the 1970s sometime, 1974. And this is the following. So let M be a compact oriented four-manifold. An Einstein manifold, so four-dimensional Einstein manifold. And then, so the Bishop-Goldberg observation said that the Euler number of the manifold must be non-negative, right? So that was what we have seen. But this can be improved to give a lower bound which is usually positive, maybe the absolute value of the signature. And yes, and so let's prove that because it's actually now also very simple with our preparations. So proof. So let me first write down the Gauss-Bonnet formula for the Euler number. So the Euler number, you remember, so this was given as 1 on 8 pi square integral over the manifold of, and then there was the scalar curvature term. There was the Ricci term with the negative sign. And there was the Weyl curvature term. So that is going to be integrated of the manifold. And in fact, I'd like to put a 2 here so that I just multiply everything by 2 so that I can have 4 pi squared here. And the reason why I do that is because I want to combine this with the Hitchin-Thorpe signature theorem. So if we write down add the Hitchin-Thorpe signature of the manifold, then this is given as 1 on 12 pi squared. So let's multiply this by 3. And we also get 4 pi squared here. And the terms that we obtained were given as w plus squared minus w minus squared. Right. So that's a combination of the Gauss-Bonnet and the Hitchin-Thorpe theorem. And now, so that's generally true for all oriented four manifolds. And now let's see, we are talking about an Einstein manifold, which means that this negative term is not here. That is 0, that's good. There's another negative term here, but this goes away with one of these because this is nothing but the w plus pi squared plus the w minus pi squared. So this cancels that. So then we are left with 1 on 4 pi squared integral over the manifold of the scalar curvature term plus 2 times w plus term integrated, which is non-negative. And so this gives me that 2 times the Euler number is larger than or equal to minus 3 times the signature. And you see, this is one of the two possibilities here. In order to get the other one, we simply subtract that here. Then what will happen? Well, then these two signs change. So now the W plus part cancels and the W minus part survives. So we have that, and that's also non-negative. So that gives me this part. And that's the proof. All right, and so in this inequality that we have the absolute value of the signature is not surprising, because under orientation reversal, the Euler number does not change, but the signature changes sign. So certainly we do expect in such an inequality that we have an absolute value here. And now this is a stronger inequality, because this term might well be positive. So let's see if we can find examples which can be, where Einstein matrix can be ruled out by this inequality, but not by the previous Bishop-Goldberg inequality. In order to do that, we need the following observation, namely, let M and N be two or be compact oriented manifolds of the same dimension. So that we can form the connected sum, and then the connected sum and the disjoint union are oriented coordinate. So in other words, we could also have used the connected sum for the definition of the addition in the coordinate ring, if you wanted. So either one is fine. All right. So the proof of this lemma is by a picture, and it goes as follows. So we start with the disjoint union. So we have the disjoint union, M and N, and we need to construct a manifold of one dimension higher, whose boundary consists of three parts, namely M, N, and the connected sum of M and N. And in order to get that manifold, we start with the cylinder over the disjoint union. Of course, now, so far nothing is gained. But now, what do you do when you form the connected sum? Well, when you form the connected sum, you remove an open bar on both manifolds, and then you glue in the sphere across an interval. And so let's do that here. So let me, okay, so let's say, color. So suppose this is the ball in M, which I want to remove, and this is the ball in N, which I want to remove. I don't remove them, I just indicate them, I color them. And now what I do, instead of gluing in the sphere cross interval, I actually glue in a solid cylinder, ball cross cylinder. So that means I attach a solid cylinder to this manifold, like so. And then, of course, things have to be rounded off to give us a smooth manifold with smooth boundary. Then you see, so the manifold connecting things is this manifold here. It also contains this. That's the manifold which gives us the coordinate. And here, this part of the boundary is the disjoint union of M and N, and this part of the boundary is the connected sum of M. That's the proof. Okay, very good. So that has a consequence for the signature. We have the corollary then, namely, if we are in a dimension divisible by 4, where we can talk about the signature. So if M and N is divisible by 4, then we can talk about the signature, and since these are coordinates, the signatures must coincide. But we already know, that's very simple, that the signature of the disjoint union is just a sum of signatures. This we have already remarked earlier. So the signature is additive under connected sums. Unlike the Euler number. Last time we had a formula for the Euler number, and when we computed that if we have to take the Euler number of the connected sum, we have the sum of Euler numbers minus 2 in even degrees. And in fact, this formula from last time shows us, now that we have this lemma, it shows us that the Euler number is not a coordinate invariant, right? Whereas the signature is. So they are really different in nature. Good. The Pondyakian numbers are all coordinate invariants. And the signature is one Pondyakian number. Whereas by the Hitchin-Thorpe theorem. Alright. Or is a combination of Pondyakian numbers. And okay, and now we can look at an example. So let's, as a starting block, let's start with our favorite four manifold, namely CP2. The Euler number of CP2 is what? Generally, the Euler number of CPN. What is it? Yes. It consists of a 0 cell, a 2 cell, and a 4 cell in the cellular decomposition. Yes, indeed. So that's the Euler number, and what's the signature of CP2? We are at it. So with the standard orientation induced by the complex structure. What's the second cohomology of CP2? What's the second Betti number? Can be read off directly from the cell decomposition that I just mentioned. It's 1, 2 cell, and no 1 cell and no 3 cell. So the signature is a 1 by 1, or the intersection form is a 1 by 1 matrix. Not many options. It could be +1 or -1. And with respect to the orientation induced by the complex structure, it turns out to be +1. All right, we have computed this, in fact. Now, okay, and now let's see if we take a look at connected sums of CP2s. So what will then happen? So let's see. If we take, let's say, k-fold connected sum of CP2s, k pieces. So what will happen? Well, we know when we take the connected sum, we have to add the Euler numbers and subtract 2. Right? At each stage we have to subtract 2. So that means if we have k CP2s, then we have k times 3. But for each thing we add, we have to subtract 2, which means I have 2 times k minus 1, because I do a connected sum k minus 1 times. Okay, so then we have k minus minus plus 2. Okay, so that's the Euler number. And how about the signature? The signature of this connected sum. Well, the signature is simply additive, so that's easy. The signature of each piece is 1, so this is simply k. And now we can check which values of k this inequality is satisfied or violated. So we have the Hitchin-Thorpe inequality. So that's my of m is larger or equal to 2/3 times the signature of that m. If, only if, well, here we have k plus 2 is larger than or equal to 3/3 times k. And so that is equivalent to saying, well, here we have 3/3 k, we subtract 1k, then we are left with 1/2 k, and here we have 2, and we can multiply the whole thing by 2, and we get 4 here. So these are the values of k for which the inequality holds, and therefore, for k larger than 4, no Einstein metric on this connected sum. And since this manifold has a positive Euler number, namely k plus 2, this would not be detected by the Bishop-Wolfram inequality, but it is detected by the Hitchin-Thorpe inequality. Okay. Further questions? Not right now. Then we move on to the next topic, which is flat bundles. Bundles can be flat but non-trivial. Flat just means it has a connection with vanishing curvature. So if a bundle is trivial, then certainly we can find a connection with vanishing curvature, but the opposite is not true. And yeah, what can we say about flat bundles? It looks like, using the theory of characteristic classes, not really anything, because the characteristic classes are represented by forms which derive from the curvature of some connection that we've chosen. So if there is a flat connection, then this should not give us anything non-trivial, right? So let's see if that is true, or in case if it is true, how can we refine the theory in order to still say something about flat bundles or vector bundles? Okay, and so to start, I want to first show that there are basically two different ways to look at flat vector bundles. One is the geometric way that we have been using over time, bundles together with a connection, etc. But there's also an entirely algebraic way to consider to look at flat bundles in terms of representation theory of the fundamental group, and I want to explain the equivalence of these two approaches, or these two viewpoints. And anyway, so throughout the section, M is a connected manifold, differentiable manifold. Right, and you fix a base point P and M, because the definition of fundamental group comes with choice of base point. So then we have I1, N, P, so that's the fundamental group of M with base point P. So these elements are represented by loops which are based, so which start and end at P. And the choice of P is not really relevant, because if you replace P by some other point, then the two groups are isomorphic. But to specify the group, I need to pick a base point. All right, and then in addition, we have the universal cover, which I call M tilde. That's the universal covering. Let me call that map pi. So we will not confuse pi 1 and pi, right? So pi 1 is the fundamental group and pi is the projection for the universal covering. And so the first observation is that actually this space M tilde can be considered as a principal bundle over M with the structure group I1. So let's see, I1 of M acts on M tilde by what's called deck transformations. How does that work? So here you have the manifold M, here is our base point P, and somehow here is the manifold M tilde, and we have these pre-images of P, projection M pi. So let's let's pick some pre-image point here, let's say P tilde. So pick P tilde, the pre-image P. And now I want to describe how this how the fundamental group acts on M tilde. And well, the elements of the fundamental group are represented by loops which are based at P. Let's say one such thing. So that gamma, it's a loop, and its equivalence, its homotopy class, I denote by the square bracket, so that will then be an element of the fundamental group. So gamma is a loop, let's say always parameterized over the unit interval. And how does this loop act on points of M tilde? So that means if I have a point x and M tilde, it must be mapped somewhere by the corresponding deck transformation. So what do? Well, you could choose a path from x to P tilde and project the path down, so then we will get a path from pi of x to P, right? We indicate by colors what corresponds to what. So this path is projected down here. And now we have a loop actually also based at pi of x. Maybe going to P, going around by gamma, and going back. So that is a loop which is based at pi of x. And now we can take that loop and lift it to the universal cover starting at x. So for the first part of the lift is obvious, as the path we started with. And then we lift this loop, and this loop will then end, so the loop ends here down here again in P, but when we lift it, it may well end at a different pre-image point. So that's something here. And now we go back, so we have to lift this orange path once more, but this will then give us, if we lift it here, some other path, because it's not starting here, it's starting there. And then the end point of that path is the image point of the deck transformation. So that's the image point of x under the deck transformation that corresponds to the loop gamma. So then there is a corresponding diffeomorphism corresponding to this one on the universal cover, and that's the thing that I've just described. So this is then tau gamma x. Indeed. So there are several things to be shown. We need to show that it does not depend on the choice of p tilde. We also need to show that it does not depend on the choice of gamma. And we also have to show that it's a diffeomorphism, but the later thing is pretty obvious because it's easy to see how we get the inverse back, maybe by taking the inverse loop here. Yeah, but these things I'm not going to do. This is a part of the standard elementary topology course. I just wanted to recall the construction. And also, it's not just that we have these different deck transformations. In fact, this means this map. So the map from the fundamental group to the diffeomorphism group of the manifold M tilde, so which maps such a homotopy class of path to the corresponding deck transformation. So that's a group homomorphism. That's easy to see. Why? Well, if you have the trivial element here, then this can be represented by the constant loop. So that means you go here, you don't do anything, and you go back. If you lift that, you go here, don't do anything, and go back. So this gives you the identity. Furthermore, if you have two loops, and you compose the corresponding deck transformations, what do? Well, you go here, you have one loop, and you have another loop, and then you go back. But that is the same thing as saying you go here, go around, go back, go again forward, and then go around, and then go back. And then you lift, both lifts yield the same thing. Because the path that you get by going forward, around, back is homotopic to the path going forward, around, back, forward, around, back. Yeah. So that shows that the composition here is mapped to the composition. And as I said earlier, the inverse is then just also the inverse given by the inverse fundamental group going backwards. So it's a group homomorphism. All right. Good. And now we have these deck transformations. And now if we have a representation of the fundamental group on a vector space. In other words, we have a whole group homomorphism from the fundamental group to the automorphism of that vector space. Then we get an associated vector bundle on M. So how does that work? So let rho phi 1 to GLN, so that in the real case, the complex case will be just the same. So let this be a group homomorphism. So, or in other words, we have a representation of this fundamental group on Rn. That's bilinear maps. That's the same thing. Good. Oh, before I discuss that, maybe I should have mentioned the following thing. So this action of pi1 on the universal cover, so this is simply transitive on each fiber. On each fiber of this universal covering. Since deck transformations, they commute with the projection map, so they just permute the elements of each fiber. And in the case of the universal covering, this map is transitive, so each point of the fiber can be mapped to any point of the fiber. And it's also simply transitive, so that means if we have two deck transformations which do the same thing on the fiber, then they are actually the same. So this is also the theory of deck transformations. But we could now call this saying that M tilde is actually a principal bundle over M with structure group pi1. So I'd like to note that. M tilde is a pi1 M principal bundle on M. And here this group, this is considered as a zero-dimensional Lie group. In other words, it's equipped with a discrete topology simply. So then everything is automatically continuous. And so now we have this particular principal bundle that we always get for any manifold when we look at its universal cover. And if we have a principal bundle, then any representation of the structure group gives rise to a vector bundle by associating this representation space to the principal bundle. And that's what I want to do now. Okay, so let rho be such a group homomorphism, then we get an associated real vector bundle of rank n, or vector bundle of rank n by the usual construction that you do when you have a representation and a principal bundle. So you take the space, so the total space of this bundle, E, is given as, you take the space of the principal bundle and you take the space on which the structure group acts. In this case, this is on n. And then, you take the fiber product over rho. And what this means explicitly is that you take the Cartesian product of the two and you divide out an equivalence relation which is defined by rho. So where two pairs are equivalent. So the first one is a point x in M tilde and a vector v in Rn. And this is equivalent to, and now I can replace x by tau g of x, where this is the action by the deck transformation corresponding to an element G in the fundamental group, which is the structure group in this case. And here I have rho G of V. So that is just rho corresponding to G, which gives me a linear map. I let this matrix, I let it act on the vector D. So this is for x in tilde, G in the fundamental group, and V in Rn. So that's the equivalence relation. Yeah, so that's I mean, this has nothing to do with the fundamental group. That's the usual construction for the associated vector bundle of a principal bundle with respect to a representation, and this was considered in one of the early exercise sheets. Okay, so we have this vector bundle, and in fact, if so, it's clear that you could replace R by C, and then here you would replace Rn by Cn, and then you would get a complex vector bundle. But you could also replace GLN R by OM, for instance. Then this would act by orthogonal maps, and then we could take the associated vector bundle and just equip it with the standard scalar product from Rn, and since that would be preserved by these maps, it would induce a well-defined scalar product on each fiber, etc. So depending on which group you precisely take here, structure group you take, you get different types of bundles that we have considered. And these are exactly the structure groups that we were looking at earlier, right? So GLN is GLNR is the structure group of a general real vector bundle. But you can do the same construction with similarly can replace GLNR by some other group G and obtain different types of bundles, vector bundles. Okay, so here's the table. So let's say G, and here's the kind of vector bundle. So G and R gives us a real bundle, vector bundle of rank R, N, sorry, rank N. Then GL and C gives us a complex vector bundle of rank N. Now ON would give us a Riemannian vector bundle of rank N. SON, what's that? Oriented Riemannian vector bundle of rank N. Okay, UN. What did that give us? Yes, emission. Exactly. Vector bundle of rank N. So it's just a complex vector bundle equipped with an emission scalar product everywhere. Yes. And what group would you have to take if you wanted an oriented real vector bundle? In order to get an oriented real vector bundle here, what would you have to take here? So here this is oriented Riemannian, but oriented without Riemannian structure. So what's the group? GL plus, yeah. So positive determinant. Empirical matrices, yes. Okay, good. So depending on the situation, you have different groups as target group here. All right. Good. So given a representation of the fundamental group, we get an associated vector bundle. And depending on the special, on which group exactly we take here, we get different kinds of vector bundles. But now I was claiming we do not just get a vector bundle, we get more than just a vector bundle in this case. And this is special now for the fundamental group, in contrast to an arbitrary principal bundle. Namely, in this case, we get also a canonical connection on the bundle. So let me describe that. So that's not true for general principal bundles and representations. In general, you do not have a canonical connection, but here you do. And how does this come out? So these connections act on sections. So maybe we should briefly see how we should think of sections of this vector bundle. And okay, so I'm saying a section of this vector bundle. So it's a vector bundle on M, right? This total space M tilde cross row Rn. Let me stick to the real case here. So if I have a section in here, I can describe this as a one-to-one correspondence to functions on M tilde with values in Rn. We call this tilde. So that's a smooth function on M tilde with values in Rn. We satisfy a periodicity condition, and that's the one we essentially comes from this equivalence relation here, namely S tilde of tau g applied to x, vector transformation applied to x, must be such that it's consistent with this equivalence relation, namely that it's rho g of S tilde of x. So this must hold for all x and M tilde and g the fundamental group. Okay, namely what's the relation? I mean, if I have such a map, then I can write down a section S. So this is this lives on M, not on the universal cover. So I can apply my section to pi of some point x in M tilde. And every point in M is of the form pi of x. So pi is the projection of the universal covering. So, and this must now give me an element in the corresponding fiber of the associated vector bundle, and those were equivalence classes. And what's that? The equivalence class? Well, the equivalence class is take x and take S tilde of x here. So this lies in my vector space. Tilde of x, so that's a pair pointing in tilde and pointing in vector space. And this requirement here makes sure that it doesn't matter which pre-image point of pi of x I'm choosing. Yeah. So this is exactly the requirement that I need in order to make this well defined. So that's the relation between a section and the associated vector bundle and a function on the universal cover with values in Rn satisfying this periodicity condition. Good. And this is useful because sometimes it's just simpler to work with such Rn-valued functions rather than sections in a vector bundle. All right, and in particular I can use this now in order to write down the canonical connection that comes with this construction. So canonical connection on this associated vector bundle. Maybe I should have written Kn because it's all the same. Well, I could describe it here on this level, or I could describe it on that level. So let me describe it on that level. And so if I want to define the covariant derivative of section S here in direction of a vector x, so that's now a capital X, and that's a tangent vector, so x is a tangent vector to the manifold M, of course. I want to define that, right? And S is a section. I can make use of this relation, namely I define it as follows. I take the section which now here is given as, so the point is, base point of this vector is q, so just take some lift q tilde, because this needs to be in m tilde, so I take a lift q tilde of q, which I choose, and then I take the derivative of the corresponding function, the usual, so that's a usual, just a an Rn-valued function, I can just take the usual derivative in the direction, now this must be a tangent vector on m tilde, right? Because S tilde lives on m tilde, so it must be a vector x tilde, where I choose q tilde such that it maps to q, and x tilde such that it maps to x. Now, so this x tilde is an element in the tangent space of m tilde at the point q tilde. So this x tilde is uniquely determined. So the q tilde is a choice, but once I've chosen q tilde, the x tilde is uniquely determined because this covering map is locally as a local diffeomorphism, so d pi is invertible. So then the x tilde is uniquely determined. Okay, and now of course we need to check well-definedness. We might well replace q tilde by some other q tilde tilde, and then we have to check that this gives us the same result. I mean, what we are doing here is of course a special case of what you are saying. So one way to put it, so well, what's a connection on the principal bundle? I mean, we discussed connections in a rather big generality at some point, and there we had these horizontal spaces. In this case, you could just say, well, the m tilde is a covering, so the tangent space is exactly the horizontal space, the vertical space is 0. So there's only one possibility to choose a horizontal space, namely the full tangent space to m tilde. And then you take that connection on the principal bundle and use it on the vector bundle. That's the same thing as what I'm describing here. Yeah, in that sense, yes. But I want to give an explicit description because we want to work with it. And so we need to, let's just, for the fun of it, check that it's well defined. So that means the choice of q tilde is irrelevant here. So that pi of q tilde and pi of q tilde tilde both in q, and then correspondingly x tilde into q tilde m tilde and x tilde tilde in t tilde tilde m tilde such that d pi x tilde and d pi x tilde tilde of x. And then we need to check that if I replace the tildes here by double tildes, then I get the same thing. And well, how do you do the differential here for such an Rn valued function? You take this tangent vector and you take a curve that represents it, and then you compose that with the curve and you differentiate. Good, so let's do that. So choose curve C from unit interval, let's say, to m tilde representing x tilde, so such that, let's say, minus epsilon epsilon, such that C of 0 is q tilde and C dot of 0 is x tilde. And then we can find, since the action of the fundamental group is transitive on the fibers, we can find an element in the fundamental group whose deck transformation maps q tilde to q tilde tilde. So choose G1 such that the corresponding deck transformation of q tilde gives me q tilde tilde. Good. All right, then if I look at the curve tau G composed with C, so that's also a curve m tilde, and it has the property that this curve, when you evaluate it at 0, this gives me q tilde, and then apply the deck transformation, so I get q tilde tilde. And if I differentiate it, at 0, then I get, this curve also maps, projects down to the same curve as C. And so this gives me a tangent vector at q tilde tilde, which is mapped by the projection map onto the same vector x tilde, but that vector is uniquely determined by this condition, it's x tilde tilde. So that's why I get x tilde tilde. Now d pi is an isomorphism. And now I can compute this second entry here. So if I differentiate my function s tilde in the direction x tilde tilde at the point q tilde tilde, then what is it? So I have to take s tilde and then insert the curve which gives me that vector, and differentiate. So that's what I have to do. That's the definition. And now I need to use this equivariance property of my function s tilde, namely that I can replace the tau g inside by a rho g outside. Let's do that. Like that. And now this rho of g is some fixed linear transformation. And differentiate, and this is a curve in this fixed vector space, Rn, and differentiation commutes with fixed linear transformations. So I can pull the rho g out. Okay, and now this one is nothing but del x tilde s tilde. So that's what I have here for the x tilde term. And so that means that if I take the point q tilde with this derivative, x tilde tilde s tilde, then tilde tilde is the same thing as tau g of q tilde. And this guy I've just computed to be rho of g del x tilde s tilde. And now the equivalence condition in my vector bundle exactly tells me that this is the same as q tilde del x tilde s tilde. So that's the well-defined system. Good. So this gives me this canonical connection in my bundle. And this canonical connection for my associated bundle is flat. That's what I'm talking about, right? So this section is called flat vector bundles. And here we have constructed not just a canonical vector bundle, actually a canonical flat bundle. And why is that? Well, what is the curvature? The curvature, so locally, the connection is, so if you go to a small patch where your projection map is a diffeomorphism, then you see that this connection is just given by the usual derivative of functions. And certainly if you apply this twice and you interchange the order of the vectors, this will not, here there will be no commutation term. So this one, the curvature of this usual derivative of functions, the curvature of that is 0. And therefore the curvature of that is 0. So it's a flat. By construction, since locally it's given by the usual derivative of functions, it's flat. Now, it's flat. So this canonical connection is flat. All right. So this, so what I've explained here is a way to construct flat bundles, right? So you look at the fundamental group, you pick a representation of the fundamental group, then you get an associated vector bundle coming from this, because the universal cover is a principal bundle with structure group, fundamental group. You associate your representation space to it, and then you get this vector bundle, and it turns out that this comes with a canonical connection, which is flat. This table, yeah, this works with also the connection is then automatically compatible, indeed. And so if this is the group, right, that's what you're asking, if this is the group, then the connection that you construct is always compatible with the structure. So that because then locally this is given as the usual derivative in Rn with respect to the standard scalar product, the usual derivative is metric. And the fact that this lands in On tells us that the standard scalar product on Rn gives us canonically a scalar product on each fiber. And since this is compatible, then this is compatible. And the same here, and yeah, so that's automatic. No, I mean, this description that I've given, you can't do that in the general case. Because here I'm really using the fact that d pi is an isomorphism. In the general case, you have these horizontal subspaces in the total space of your principal bundle. And if curvature occurs, this is related to the fact that this horizontal distribution is not integrable. So you can have horizontal curves which project to closed curves, but which are not closed upstairs. And then this vertical part is what gives rise to the curvature. But here we don't have a vertical part. Right? The fibers are discrete, so the tension spaces, the vertical tension spaces are 0. But the way I describe it here, this is something that way you cannot do it directly. Yeah, well, that's one way to view it. So the curvature comes from the vertical part of the bundle, the vertical bundle, and this is 0 here in this case. Okay, good. Anyway, so we have these flat connections coming from representations of the fundamental group. And now I want to explain why the converse is also true. If you have any flat bundle over a manifold, it must arise this way. So understanding representations of the fundamental group is really the same thing as understanding flat bundles. This is why flat bundles are interesting to algebraically minded people who want to understand representations. No. Okay, so let's do that. So let's start conversely. Let F be a, let's say, R vector bundle of rank n on the manifold M, equipped with a flat connection. Blah blah. And now somehow out of this, I have to construct a representation of the fundamental group, right? Let me do that. So we have this base point P at which we take a fundamental group, and so associate it to loops, or rather to homotopy classes of loops based at that point. I need to associate an element in some GLN in this case. Right? And well, what can I do? There's actually only one thing that comes to one's mind. So let gamma represent a homotopy class phi1. I always assume that the gamma is smooth, or at least piecewise smooth. So on a manifold, that's no restriction. So in the general topological theory, these are continuous paths, but on a manifold, you can also take smooth paths if you want, or piecewise smooth paths. So every element in pi1 is represented by a smooth path. We just apply a smoothing modifier to a continuous path. This will not change the homotopy class and give you a smooth representation. So the reason why I'm saying this is because if I have a smooth path here, so gamma or piecewise smooth path, at least, so this goes to M, and it's based at P. And now what I'm doing is I'm looking, I have a connection here, so I'm looking at parallel transport along this path. So let's see. So we have this parallel transporter, 0 to 1, along the path gamma. So what does this give me now? This is a map that maps points at the initial point of gamma, which is Fp. So gamma of 0 is P, and gives me an element at the target point here, which is gamma of 1, which is also 1. I have that. And it's in fact a linear map, because it's a connection on a vector bundle. So this gives me a linear isomorphism. That is good. But in general, parallel transport is not compatible with taking homotopy classes. So if you replace gamma with some homotopic path, parallel transport will in general change. However, here we are in the flat case, and then it doesn't change. So that's the next lemma. And this is where flatness enters the game. nabla flat implies that parallel transport along gamma or gamma check is the same if gamma and gamma check are homotopic. And here, so represent the same homotopy class. Let me write that. So it means homotopic with fixed endpoints. Okay, so why is that? That's what we need, because then parallel transport is really defined by something which comes from the fundamental group, not from the actual path. Good. All right. So well, if I let U be an element in that fiber Fp, and now if I take parallel transport along gamma of that element, parallel transport it maybe not all the way up to t equal 1, but just to some t for the moment. And then, by definition of parallel transporter, this is parallel in t, right? This is a parallel section along the path gamma. So if I differentiate this with respect to the covariant derivative, then I get 0. That's the definition of parallel transport. And now, let us look at a homotopy. Now, let gamma S be smooth homotopy from gamma to gamma hat to gamma check. So that means each gamma S represents the same element, of course, in the fundamental group. So it's a smooth path. Then same base initial points, end points in P, and gamma 0 is gamma, and gamma 1 is gamma hat, gamma check. So it's deformation from the one path into the other. And if I now look at this equation for gamma S, so differentiate it, and then I get 0. And I can differentiate once more in the S direction, and it's of course still 0. Now, let me turn these two derivatives around. But then there is a correction term. I cannot just commute covariant derivatives. And the correction term is, of course, just a curvature. So here I have the derivative of gamma S in the S direction. Let me call this gamma S prime. So the prime stands for the S derivative. And here I have the T direction, so it's gamma S dot applied to P0T gamma S of E. And but here we have assumed that the connection is flat, so this correction term is actually not there. So that's the general formula, but in our case there is no curvature, so that's 0. So that tells me that this double derivative is 0. And now, if I look at this inner term at a special value of t, namely t equals 0, then what do I have? Well, the parallel transport from the point to itself, I mean, then I am not doing anything, no matter what the path is here. Then this is just the identity, so that is just u, but that doesn't depend on s, so that is 0. So we see for t equals 0, this term is 0, but then it's parallel. Therefore, it has to be always 0. So these two things together imply that this s derivative is 0 for all s and t, in particular for t equals 1. And therefore, and now this, remember the gamma s again ends up at p. So that is really a curve. So this is a curve in fp. So the endpoint of all these curves gamma s is p. So this is some curve in the fiber fp. So this covariant derivative is actually the usual derivative in that vector space. And it's 0, and so therefore it must be the same for s equals 0 and s equals 1. So therefore, p blah blah su is not constant in s, hence p10 at 0 we have gamma, and at 1 we have gamma check. And this holds for each u, and so the parallel transport is the same. Good, so that's the proof of the lemma. And so this flatness of our connection allows us to consider this parallel transport as something which depends not on the actual path gamma, but only on its homotopy class. So therefore, P1 gamma from Fp to Fp depends only on the homotopy class 1 by 1. This map, linear map. So we obtain map rho from pi 1 to the automorphisms GLP induced from this, such that rho of the equivalence class of such a path is exactly the parallel transport of path. And this is in fact a homomorphism. So rho is a homomorphism. Well, if you have a trivial element here, then you can represent it by the constant path, and parallel transport of constant path is the identity. And if you compose two elements in the fundamental group, if you multiply them, this corresponds to concatenating the path. And we have earlier seen parallel transport of the concatenation is the same thing as the composition of the parallel transport. So this follows directly from what we know. So that's good, because now, starting from the vector bundle, and we have constructed a homomorphism from the fundamental group to GLFPN, and now we can choose any basis in FPN to identify this with GLN. If you want. Good, but now we still have to convince ourselves that this construction is really the inverse of the previous construction. So if I start with, let's say, a vector bundle, and I do this then I with the flat vector bundle. Then I get this representation rho of the fundamental group, and then I can do the first construction and can construct a vector bundle out of that again. And I need to check that I get the vector bundle back that I started with, right? Up to connection preserving isomorphism, of course. And why is that true? Let's see. So suppose we start with this flat vector bundle F, and we get this representation rho. And now, how did the construction go when I have a representation? Well, I was going up to the universal cover and then associating my representation space to the universal cover regarded as a type 1 principal bundle. So let's see what happens if I take this vector bundle F and just pull it back to the universal cover first. So pull back, let me call the pullback F tilde of F to the universal cover. I can certainly do that. And I'm claiming that this is canonically trivial. It's not just trivial, but it comes actually with a natural trivialization. Why? Well, if you look at the fiber of that bundle at some point x is a point in the universal cover, then, so here's my universal cover, M tilde, here's my point x, and here's my preferred pre-image point of P, the base point of that group. Now what you can do is take a path, choose a path, gamma, from x to P tilde, and parallel transport along it. So then you can do the parallel transport along this path gamma and end up in F tilde P tilde. And sure enough, this is an isomorphism. And now this map does not depend on the choice of gamma, because on the universal covering, all paths are homotopic. And we saw earlier on a flat bundle, so if I pull back this bundle together with its connection, otherwise I couldn't talk about principle of parallel transport here. Here everything is homotopic, and therefore this map is actually independent of any choice of gamma. Not just of its homotopy class, because there is only one homotopy class, right? M tilde is simply connected. So that's independent of anything of the choice of gamma. And so we have this canonically given isomorphism between the fiber at any point to the fiber at one specific point. And that's the global trivialization. Good. Independent of gamma, right? All paths on tilde now are homotopic. That's the reason. Good. And now we have this canonically, so if you pull it back, it's a canonically trivialized bundle. And so it's basically the bundle M tilde cross this particular fiber here. And remember how we constructed our bundle earlier. We took M tilde cross the fixed vector space, and then we divided out an equivalence relation. And so we just have to check that the equivalence relation that we divide out gives rise to the original bundle F on M. So, okay. So how did we construct our bundle out of the representation? Okay, so we said, all right, so if we, what's the fiber at a point x? Well, we look at all pre-images of x. This guy's down. And then I look at the fibers over this, and I have this identification given by the depth transformations. Now, if I have two different points here in the pre-image of x, I should call this q to be consistent, because earlier x was a point in m tilde, and p and q were points in n. So now I have these pre-image points, q tilde, etc. And so the fiber over q was given as this equivalence relation of the fibers over here with the equivalence, with the identification given by depth transformations and the representation that I'm using. Good. Now if I have two different pre-image points here, let's say q tilde and q tilde tilde. Now, what can I do? I choose a path from q tilde to p tilde and choose a path from q tilde to p tilde. This gives me two paths if I project down from q to p. Okay. And the f p tilde, that's by definition of pullback bundle, that's the same thing as fp. So how do I identify the fiber here and the fiber there to give me the fiber here? Well, I do parallel transport along this path, doesn't matter which one I take, and go backwards with this path. So this gives me a map from here to there. That's the identification. So, and this parallel transport is exactly, by definition, the action of my representation rho here. Right? So, if I now pass to the quotient q tilde, comma some vector v in here, and I want to compare this, so I want to map it to the original bundle, so that's the associated, so that lies in the associated bundle here, and I want to identify this bundle with my original bundle F. Right. And the total space of this bundle. So that is the total space of this bundle. And what do? Well, I project, so that lies in here. So I take the parallel transport along this curve gamma backwards up to V, and evaluate, project this down to that point. So that is this element. So that's an element of f tilde q tilde, which by the definition of pullback is nothing but so that's the method. And now if you replace q tilde by some other q tilde tilde, then the difference will be, this will differ by parallel transport along a closed loop that I've indicated here. And this is exactly the equivalence relation which is by this representation. Okay. All right, so that's the equivalence of bundles with a flat connection and representations of the fundamental group. So the aim is now to understand flat bundles a little bit better. And the question is, can characteristic classes be helpful in this? So we'll discuss this on Thursday. Thank you.